So ideal solution, I think all of you got a hang of. Like we took example of benzene, toluene. Essentially, even if you mix, there's not a lot of difference in the interactions. Now, what do we mean by interactions? So for that, let's look at examples of non-ideal solutions. So another example that I was looking up abhi, they took the example of carbon disulphide, CS2, and acetone. So acetone, I'll just put the structure also. Okay. Let's take carbon disulphide first. So carbon disulphide, what sort of a molecule is it? Polar or non-polar?
Polar, right?
Non-polar.
Okay, we have two answers. Polar or non-polar?
Polar.
Okay, Sanskriti, Smera.
I think it's non-polar because like organic stuff dissolves in it.
That's a good logic, good way to figure it out. Think of the structure also, no? Carbon had like CS2, carbon disulphide. So the structure kaise rahega? What sort of bonds will be there?
It cancels out, so non-polar.
Huh. Linear, and carbon doesn't have any more electrons, so pura linear 180 hoga. And even if electronegativity difference is there, cancels out, opposite, equal and opposite. So this is non-polar. So if carbon disulphide is non-polar, इसमें go back to what you studied in grade 11. किस तरह के intermolecular forces रहेंगे? What all forces will you find here? Van der Waals to default सब में रहेगा, the London dispersion. ठीक है. Apart from that, would you have any
Dipole-induced dipole.
Dipole-induced.
dipole-induced dipole के लिए? Is there anything that is inducing dipole in carbon disulphide? कोई भी pole नहीं.
There will be no dipole now because it's non-polar.
Yeah, there's no dipole at all. So dipole nahi hoga. Hydrogen bonding won't be there. Nothing else. Like just normal London dispersion van der Waals forces will be there. Okay, now take acetone. Similarly, see if it is polar or non-polar and what all types of forces will acetone have. Van der Waals is default. That I'm writing down. What else? So carbon, 3 sides. So sp2 carbon hai, matlab like structure is like this. Yahan pe you have a CH3. Yahan pe you have a CH3. Both are electron donating. Like even though it's carbon-carbon, you kind of have those electronegative properties.
Dipole-induced.
हाँ, dipole-induced dipole नहीं, direct dipole-dipole interactions रहेंगे. So one acetone molecule is polar. Every acetone molecule is going to be polar only, no? So whatever interactions are there, they're basically dipole-dipole interactions.
This acetone is a polar compound, right?
Huh.
So when we were doing Finkelstein, that time you made us write dry acetone is used as it is a non-polar solvent.
In terms of polarity, again, it's not as polar as water. Like the polarity is not as high as water, but there is going to be a slight amount of polarity between carbon and oxygen. Again, polar, non-polar is not black and white. Like again, it depends on how much of the charge separation is there. What is the difference between the electronegativities? So you use dry acetone because again, like it is not capable of ionizing salts and acids and bases and all that. But objectively, if you look at it, it is definitely a lot more polar than carbon disulfide, jahan pe whatever polarity is there is completely cancelled out.
Yes, that does not sound believable at all.
What do you mean?
You too. Before you said it's non-polar solvent. Now you're saying it has polarity. Is it non-polar or?
Again, context matters. So it is an organic solvent. It is not polar enough to ionize, like cause ionization and dissociation and all of that. So for that reason, like if you're using,
In Finkelstein, we use triacetone because it's a non-polar solvent and it basically dissolves the NaX, right? So, and it favors forward reaction.
No, it doesn't. Okay, you use triacetone non-polarity in that context. The NaX precipitates out so that you don't have the backward reaction taking place. If you use water, the NaX is going to ionize. So that's what I meant by, like, see, if you take water, water is extremely polar. Water associates ions. It is capable of dissolving the salts, breaking them down into ions, like most of them. Again, like calcium carbonate and all don't dissolve in water, but yeah. But instead, yeah, so if like NaX is a byproduct and you want to prevent the backward reaction taking place, using something like water or acidic medium, basic medium is something that is capable of dissolving and ionizing NaX is not going to help with your forward reaction. So that is why you use dry acetone, because for the sake of that reaction, it is basically non-polar. It's not as polar as something like water. Like NaX precipitates out of dry acetone. It won't dissolve in dry acetone.
Is this why we say that acetone dissolves both polar and non-polar solutes?
Yeah. So that's why, again, it's not like black or white. It's a spectrum. It, like, again, when we talk about polarity, that's why you have a specific quantity called dipole moment. If dipole moment is high, it's extremely polar. If dipole moment is extremely low, it is basically non-polar. And there's like things in between also. Okay.
But how can the dipole moment change based on like situation to situation? It
won't
for
change
one acid
on no, like dipole moment for a particular compound will be the same. Like acetone का एक dipole moment रहेगा, water का एक dipole moment रहेगा, ammonia का एक dipole moment रहेगा, that way.
Ma'am, so if in Finkelstein's reaction, if acetone is used to precipitate out, is used to dissolve NaCl, then NaCl is
The
polar.
opposite of
So,
dissolve. It won't dissolve
Oh.
NaCl. Yeah, it precipitate out. So that the backward reaction will not take place. So you don't have those Cl minus ions. You don't want that displacement happening. What happened, Arya? You look like you don't like what's happening.
I didn't. Yeah, I think it's a bit confusing as to how the same compound can be called non-polar in certain circumstances, even when it has a small amount of dipole, but in another situation it can be called polar, again because of the same dipole.
Again, we're not like defining acetone as, oh, it is completely polar, non-polar. It is, again,
But see, if it has, like, if acetone has a small amount of dipole, there are other organic solvents. So why just acetone in Finkelstein? Like, we could use any other solvent.
that is why a lot of reactions also use dry ether for those sorts of purposes only. But there are organic solvents that you use in different situations. So Finkelstein, when, again, it's a named reaction, right? So that is the reaction that a person has performed, and you guys are learning the basic thing. Again, with time also, like, there's a lot of variations to these same reactions. also, like if somebody else figured out that, oh, if we use the substance, the efficiency is a lot more, oh, this has an added advantage and things like that, there are variations, of course. But
Is there a difference in polarity of dry and not dry compounds?
so we use dry to establish the like we want to ensure that like we don't want to, okay, how do I explain this? So dry, not dry. So we specify that we want dry acetone or dry ether to ensure that we are not using a solution of it, or we are not mixing something like alcohol. Again, alcohol has extremely high polarity, which is why it is capable of dissolving in water also. Lot more than acetone for sure. So things like that. So there is a difference between dry, like we mention, say, as using dry acetone, dry ether to explain the circumstances, the criteria, the reaction conditions essentially, so that we don't have any ionization taking place there.
Ma'am, why does I don't understand, why does dry acetone have to be a non-polar solvent for Finkelstein?
Because if you use something, like you don't want the sodium salt to ionize, NaCl, NaI, whatever that is, like NaBr, whatever is produced. You want to precipitate out so that one product is removed and so that the backward reaction does not take place.
I'm still confused.
So what happens if you put NaCl in water?
It gets dissolved.
What happens when salts dissolve in water?
Water causes Na plus and Cl minus to break because
Ionization.
it has a high dye. Yeah.
Right? And once you have ions, which are charged particles, they'll immediately get attracted to opposite ions. In water, they'll remain dissociated because I'd explained yesterday, right? Hydration. The water molecules basically surround those ions. They'll remain dissociated that way. And that is the whole reason why double displacement reactions take place. The opposite ions get attracted, and if they're insoluble in water, they precipitate out of water. So tabhi we say that, okay, ye wala reaction has taken place. You can see that product being precipitated out. Now, if we use some other solvent other than water, so that that salt doesn't break down into ions, you can ensure that those ions will not further react with something else in that solution. You can ensure that the reaction is being pushed forward, backward reaction is being prevented.
No, but what does the polarity of the solvent have anything to do with that?
Ionization, right? Like ions, why does ionization take place? They don't spontaneously be like, oh, medium has changed, let's break into ions. The medium is causing those ions to break down. Water is polar and it is extremely highly polar. That is why it is capable of dissolving these salts, dissolving ions, acids, bases, all of these.
So now, okay, so if
And
the solvent,
hold that thought. Like that is the reason some salts are soluble in water and some salts end up being insoluble in water, because even
correct,
the quantity of water is not enough to break those bonds, like barium sulfate, silver chloride, and calcium carbonate, and things like that. The KSP values and all that we studied about.
and does that depend also on the polarity of the solute?
Yes. It like if you get down to it, it all depends on the energies. Like if that
Like how strong the bond is.
Yes. So if that hydration energy, solvation energy is like sufficient to break that bond, yes, it will break. If it is not sufficient to, break it down, then it won't. And then we'll see it as, oh, this has not dissolved. This has not happened. That way.
So now for Finkelstein, dry acetone, we would, as you said, that we would consider that to be
It's not polar
not,
enough to break that. Yeah.
it's not polar enough.
It's not polar enough to break those bonds.
No, we wouldn't call it non-polar. We would just call it not polar enough, right?
Yeah,
It's still
but
polar.
the whole point is, in that context, for that particular salt, it is essentially non-polar.
Basically, the polarity is less than what we need to break the bond.
Yes.
Okay, understood.
Yeah.
So when we talk about acetone as like a molecule, it is polar.
Absolutely.
Right?
Yeah. Okay. There's a slight polarity here again because carbon and oxygen electronegativity difference. But again, like end of the day, rest of the molecule is all organic, right? So these are not contributing to all of this at all. So less polarity, but still compared to carbon disulphide, तो थोड़ा सा तो है. And okay, so यहाँ पे it's completely non-polar. Like this has its own set of interactions, which is van der Waals. Acetone में you have dipole-dipole as well as van der Waals. Now, when both of them are mixture में, if you have carbon disulphide and an acetone molecule interacting, so apart from their regular van der Waals interactions that they have by default, क्योंकि दोनों molecules have, additional you're going to have dipole-induced dipole interactions. So why dipole-induced dipole? यहाँ पे like acetone has a bit of polarity that is going to induce a little bit of dipole in CS2 when they both come close together. You guys remember dipole-dipole and dipole-induced dipole interactions? No? Okay. Dipole-dipole, though, you guys got like know what it is, right? So dipole-induced dipole mein, so this occurs when
Dipole is when like there is a dipole when there is a polar molecule and that will induce dipole in a non-polar molecule that it is bonding with.
correct. Yeah.
And it's a very weak bond.
Yeah. So polar hai. If it comes close to a non-polar, it's not polar because the charge is equally distributed throughout. But when this comes, your negative charge is going to repel the negative charge. So it's going to induce a small amount of dipole here because of the proximity. So the polar is already there. And यहाँ पे, because यहाँ पे negative charge hai, the negative is going to go slightly away and it's going to attract the positive slightly towards this side. Okay, so the dipole is going to induce, a polar molecule is going to induce the dipole moment in non-polar, and immediately, again, it is completely only because of the proximity. As they are moving, once they go far away, this again becomes a non-polar and this will go annoy another non-polar molecule that way. Yeah. So that's basically dipole-induced dipole interaction. Okay, now let's compare individual interactions versus the mixture ka interaction. So if you compare dipole-dipole versus dipole and induced dipole interactions, which one is stronger and which one is weaker?
Dipole-induced dipole is weaker.
This is a weaker interaction, right?
As compared to
This in each
Yeah.
dipole. Yeah, dipole-dipole.
yeah.
So when you combine, like when you have a solution of CS2 in acetone, pure acetone the interactions are stronger compared to this particular solution of carbon disulfide in acetone, right? Because this is a weaker interaction, the molecules are not held together as closely, like they are not attracted to each other as strongly as your component molecules. So this will result in, okay, so because of this, what do you think will happen to the vapor pressure of the solution? If you compare vapor pressure of acetone alone versus vapor pressure of solution, which one will be able to vaporize more better?
Dipole-induced dipole.
This will be more like it will vaporize more, right? Solution ka. So when when they did the experiments, they were looking at the vapor pressure values and all that. They found out that, see, ideally, if Raoult's law was followed and everything, it's supposed to be a straight line essay. But what ended up happening is, the vapor pressures were slightly greater than expected. So it's kind of looked this way, the graph solution. Okay. So there is a deviation from Raoult's law, right? So that is why that's an example of non-ideal solutions.
Ma'am,
Yeah.
Okay,
sorry.
go ahead.
Okay, so
this-
can I ask?
Yeah, go ahead.
So one of them is van der Waals force and other is dipole. So in this case, both of them are weaker than what is in the solution, like the force of attraction which is in the solution, like between CS2 and acetone. Like in the, when you gave the notes, you said that AA and BB. So do we like combine and consider them, or do we consider it separately? Or if AA is stronger and BB is weaker, then how do we go about it?
So that's what, like, again, overall, like, because you can't really you can't practically measure the exact value of the forces, right? So conceptually, like logically, if you were to explain why this deviation is occurring, then we can say that, okay, the interaction is not the same. Like originally, if you had individual AA interactions, BB interactions, the AB interactions, they are dominating in the sense that they're either stronger than the individual interactions or weaker than the individual interactions. So like that is just an explanation of, okay, why is it happening? But deviation from Raoult's law, like you'll get to know, okay, what is going to happen when you actually measure the vapor pressure and you find out that, okay, this is showing
This can be,
deviation, this is showing a negative deviation that way.
this can be quantified only by measuring the vapor pressure.
Yeah.
Okay. But like, what if AA bond is strong and BB bond is weak? Is it possible to have AB bond weak?
That again will also you'll also have to look at what is the composition. Again, if you add only a tiny amount of the solute, you're not going to find so much of a deviation. Only if it was comparable, then you'll be able to find a large amount of deviation as such. So lots of factors at play here, and this is like an extremely simplified, that's why we're not going into numericals and all. This is more of an introduction level key. Okay, if we have non-ideal solutions, what is the reason for that? Intermolecular interactions, attractions and repulsions, that's what is causing it. And non-ideal matlab, you have two different, either they can deviate positively, that happens if it was a weaker interactions, like the molecules are pushing away from each other, which is why you end up having a greater vapor pressure. Or you may have a negative deviation, in which case the graph is going to look something like this. So this is when the interactions are stronger. So apart from A attracting A, B attracting B, AB are also attracting each other, which is why they won't vaporize as easily. So measured vapor pressures will be lower than if it was ideal, expected.
Miss, in the previous slide, you compared vapor pressure of acetone and vapor pressure of, yeah, what have you written in between?
CS2 plus acetone.
No, like vapor pressure of acetone.
Oh,
Uske
versus.
baad, what is that?
Versus.
Versus. What was that for?
So I was just like, I was comparing. Okay, if you had pure acetone versus,
And then you said solution ka will be more, na?
yeah.
Yeah. Thank you.
So like note down the notes, Abhi, like I'll give it properly. Abhi, like, is it clearer now? Do you guys get a hang of non-ideal? Matlab, why would it deviate from Raoult's law and all that? Okay, just to summarize. So if we have non-ideal
Can
solution,
you explain positive and negative deviation?
yeah. So once let's cover up non-ideal summarize karke, then we'll go specifically in positive deviations. We'll look at 2-3 examples, and we'll go specifically in negative. We'll discuss 2-3 examples. We'll do all of that. Okay. Non-ideal solutions. So they don't obey Raoult's law. Over the entire range of concentrations. Also, what is observed is the delta H of the mixture is again not equal to 0. Matlab energy will be released or energy will be absorbed even when you're doing the dissolving thing. That's what you observe when you dissolve acids or bases, right? Small amount of energy will be released. Hydration energy, solvation energy, whatever it may be, depending on what compounds you take. Also, the mixture is, you're going to find a small amount of expansion or contraction of the mixture. So if you add 150 ml of component A and 150 ml of component B, the overall volume, if you find it, it won't be exactly 300. It may be slightly like 301, 302 ml, or it may reduce a little bit like 295, 298, 297 ml, that sort of thing. So there's going to be a difference. It's not equal. Now the why of it, why doesn't it obey Raoult's law? Why is it there? Okay, before that, let's look at, so non-ideal, there are two types. If they don't obey, there could be a positive deviation from Raoult's law, or there could be a negative deviation from Raoult's law. So positive deviation may the actual values are greater than expected values. Let's say, so this is partial pressures, vapor pressures. This is the mole fraction. So if this was the ideal case, positive deviation may, this is the actual range of vapor pressures that is observed. Solution may, both their vapor pressures are greater than expected. This is the kind of graph that you find. And negative deviation may, it's the opposite. The values of vapor pressure are less than expected. This was if it obeyed Raoult's law, negative deviation may it's lower. These are the kind of graph that is. Okay. So you can see values higher than predicted. And negative deviation may vapor pressure values are lower than predicted.
Can we be asked to draw the graphs?
Yeah. So you'll get only like again, you need to know the concept that okay, positive deviation matlab graph kaise dikhega, values will be higher than expected, that sort of a thing. Again, all of this you have it at a very theoretical basic level. So you just need to know what is what, where it occurs that way. Surface level. Ekdam.
So when is it positive and when is it negative?
1 second, just a moment. Just look at the proof. Sorry about that. Huh. So, Sia, you were asking when is it positive, when is it negative? When is it positive, when is it negative in the sense?
Like AB interactions are stronger than what is it?
Huh. Yes. So, vapor pressure higher hona chahiye, matlab the particles are able to get into vapor easily. So, they're not being held by the solution. Matlab interaction should be weaker. Okay. So, in this case, you get positive deviation when AB interactions, like the mixture may interactions, are weaker than if they were not in mixture, than if they were in separate values. So weaker than AA and BB. Is it visible or should I do it in the next next page?
It's visible.
Visible ना? Okay. And यहाँ पे negative deviation, vapor pressure कम है, मतलब the molecules are not going into vapor state, मतलब they are held tighter, meaning AB interactions are stronger than their individual things.
Ma'am,
Hmm?
in the exam, can we be given like two components and then they can say ki batao if this is if when they mix if it's ideal or non-ideal, and like do we have to explain?
Explain again, not at a deep level. Like again, there are a few examples that are given, so I am going to give you guys some examples. Then you need to know which mixtures are positively deviating, which are negatively deviating. And even if you were to ask for explanation, you can simply just state this fact. So interaction between, like जैसे CS2 acetone का किया हमने, you don't even have to go into dipole induced dipole and all of that. Just say the intermolecular attractions or interactions between both of these are stronger in this case or weaker in this case. Okay, so once you finish noting this, I will give you the examples. Right, like weaker hai. So it is easier for the molecules, because it's weaker, it is easier for the molecules to escape out in vapor phase. In this case, the tendency to escape decreases. So इसलिए इतना vapor नहीं है.
The in the graph, the upper, the line which is joining to both the points signifies what?
Joining both the points, matlab which
In both the yeah that one.
this is the actual measured value. So the dotted line is supposed to be a straight line. So this is if it was ideal, like if you just apply Raoult's law, ऐसा होना चाहिए था. But in reality, this is the measured values. You're getting greater values than the predicted values.
No, but like how did we get to the what is like joining them?
This one.
That line. Yeah, like how
These
did
are
we
measured vapor pressure values. इतना सा concentration है तो vapor pressure कितना है? अगर इतना concentration है तो what is the vapor pressure? When the concentration is this much, then what is the vapor pressure?
okay.
It's supposed to be a straight line, but because it is not ideal, it's not a straight line. It's higher values or lower values. Okay, सबका हो गया? All right. Then we figured out the why of it. Examples will continue, like same positive or negative deviation का. So यहाँ पे positive deviation left side है ना? Positive deviation. So one is CS2 and acetone. Then you have ethanol plus cyclohexane.
This is for positive, right?
All of these are positive. And we have acetone plus benzene. And negative में chloroform and acetone. Either acetone or diethyl ether. So chloroform and diethyl ether also same thing. The negative deviating thing. Phenol plus aniline. H2O plus nitric acid. Nitric acid is given, but generally any acid-based solutions show negative deviation. Yeah. Few examples, just in case you may be asked to give examples of positive deviating solutions or negatively deviating solutions. Or you may be given one of these and asked, okay, like what would you expect? Is it a positive deviation or is it a negative deviation? Or you may be asked indirect question also. You may be asked, okay, a solution of phenol and aniline, what would you expect the vapor pressure to be, or like greater than so and so value or lesser than so and so value, that sort of a thing. So few more differences in characteristics. Again, these are derived from what we discussed earlier. So positive deviation may vapor pressure values are higher, right? So P1 values are greater than the P1 naught into X1, and P2 values are also greater than P2 naught X. And in this case, it's the opposite. Because the values are lower, it's a negative deviation. So P1 and P2 will be less than what Raoult's law predicts. इसमें repulsive forces है. So the delta V mixture is greater than 0. Slight expansion. You'll observe slight expansion. इसमें you'll observe slight contraction because stronger interactions like pulls it all together closer. And typically, the delta H mixture is also greater than 0. So when you mix them, they're endothermic solutions. And यहाँ पे, because they're interacting with each other, attractive forces है. So yeah, this usually is exothermic. Delta H mixture is less than 0. As a consequence of this, because this is endothermic, heating the solution increases the solubility. And heating decreases the solubility in this case.
Can you explain the P1 point and the delta V point?
Huh. Refer to the graphs. What do you observe in the graph? Like, what do you infer from this? So straight line represents, like if they follow Raoult's law, graph ऐसा होना चाहिए. So this is the range of vapor pressures over this whole concentration, like depending on how much of each component you have. Lekin that's not the reality. Like in reality, if you measure it experimentally, this is what was observed. Isliye there was a deviation. So if you compare observed value versus Raoult's law ka value, how do they compare? Like observed values are greater than Raoult's law values, right? So that is why it's called a positive deviation, increase hua. So this is what we put it mathematically. So according to Raoult's law, this was the mathematical equation, right? Partial pressure is equal to the partial pressure when it is purely that particular component times the mole fraction of that particular thing, right? So this was Raoult's law. Lekin it is not equal. Not equal matlab either it will be greater or it will be lesser. So positive deviation may you observe that measured values are greater than what Raoult's law states, and negative deviation may it is lesser than what Raoult's law states. Okay. And delta V mixture is greater than 0. So basically, again, the particles are slightly repelling, right? Like weaker interactions hai, matlab they're pushing each other away. That's why vapor pressure bhi zyada hai. So if they're pushing each other away, it's like if you mix 50 ml of component A plus 50 ml of component B, ideally 100 ml aana chahiye. But because the particles are, because the interaction is weaker, they're slightly pushing each other away. It's not 100 ml anymore, it's slightly greater. You end up with 101 or 102 ml, that sort of a thing. Okay, so the volume of the mixture compared to adding the individual volumes, you find that volume of the mixture is slightly greater. So delta V, change in volume, is greater than 0. So overall volume is slightly increasing because of those interactions.
Because the interactions in the mixture are weak, that's why the volume is increasing.
Yeah. Okay, so stronger interaction jitna tha, it was supposed to be 50. Lekin if they're like pushing each other away, 50 se thoda zyada ho gaya because of the weaker interaction. So overall volume increases.
Ma'am, I had a question. So, in this case, you said that the deviation would just be 101, and that would make us say that it's a non-ideal solution, right? So even if there's like a small difference, we can conclude that. But then when you gave the example of benzene and toluene, you said that CH3 is like, even CH3, you said it's like a very small difference between
Again,
benzene
this
and
is
toluene.
like, it's not an actual, it's a hypothetical value. I just gave a number to explain to you guys. ऐसा नहीं होगा कि 100 का 150 हो जाएगा, इतना ज़्यादा difference नहीं होगा. It'll be a tiny.
But then it is a small deviation, right?
Yeah.
So when you compare benzene and toluene, how do you call it ideal? Even CH3 makes a difference, right?
It does not. Again, measured values, if there was so much, like itna difference agar hai, so it is going to come under non-ideal. Delta V mixture will not be equal to 0. So there's a difference between 1 ml versus 0.00001 ml, right?
Having a CH3 will definitely change the like.
But it's not a measurable difference.
Okay.
It's not like significant enough to come up on in the measurements and things.
Can you show the graph? Like,
Yeah.
can you go back? So in the first one, in positive, if AB interactions are weaker, so how is the vapor pressure more than like the
If
solvents?
interactions are weaker, what do you think will happen to the tendency to vaporize? Will it be easier for the molecules to escape out, or will it be more difficult?
Easier.
Easier, no? So if it is easier for the molecules to escape out, will more number of molecules escape out? Yes or no?
Yeah.
So more number of molecules, matlab, how will that affect the pressure in the vapor phase?
Okay, yeah, it will increase.
Okay.
Thank you.
So same thing, opposite thing in the negative deviation. Stronger interaction, they're held tighter. So if they're held by the solution, they can't escape out easily enough. Okay, so that's why measured values are lower than ideal. And delta V also, it's the same thing, like they're held tighter together. So it like there's a slight contraction that it's observed. Have I given examples for ideal solutions? Did you note down examples for ideal? No? Okay. So apart from benzene, toluene, a couple, like I'll give you two more. So you have three examples in each case. State. Ideal solutions के examples. We have benzene plus toluene. Then we have bromoethane plus chloroethane. Similarly, bromobenzene, chlorobenzene also. Then we have N-hexane and N-heptane. So it's kind of easy to figure out कहाँ पे ideal होगा. There very small difference in molecular mass and characteristics wise also pretty much they're very, very similar. Okay. So should we go to the next part, next topic?
Miss, could you, the last one was N-hexane plus?
N-heptane.
Yes, Miss, thank you.
Okay. Now, non-ideal solutions, we get like, because again, non-ideal solutions, because of how they exist, how they behave and all, they result in something called azeotropes. Okay. Azeotropes are constant boiling mixtures.
Ma'am, could you go back just a second?
Yeah, one moment.
No, like before this. Yeah.
Azeotropes, like basically constant boiling mixtures, are called azeotropes. What are they? What do you mean by constant boiling mixtures? Definition statement says, so they are binary mixtures having the same composition in liquid and vapor phase and boil at constant temperature. Okay. So these sort of mixtures are called azeotropic mixtures, or you can just call them azeotropes. So let's look at it step by step. Okay, like once you guys are finished writing, then we'll pick this apart. Figure what it is. Right. Kaveri, Smera, or Sanskriti is still noting down.
Done.
Okay. All right. So yeah, Smera.
Yes, ma'am, I had reacted.
Done.
No. So we'll start discussing. Okay, Arya is noting. हो गया? Okay. So azeotrope mixtures, they are binary mixtures. So binary matlab you have a mixture of two things having the same composition in liquid state and vapor state. Okay, so it's basically say you have it's a solution. Solution में you have component A plus component B. इसका एक composition होगा ना, like let's say component A is 0.4 mole and component B is 0.6 moles. Mole fraction 0.4 0.6 है mole fractions. Then इसके ऊपर vapor phase में भी if they have the same composition, if you measure number of moles of A, number of moles of B, the mole fraction is still 0.4 0.6 only. So those sort of mixtures are called azeotropes, and the composition in liquid state and vapor state, they are the exact same, and they boil also at the constant temperature. Boil matlab kya? So boiling is when the vapor pressure is equal to the atmospheric pressure, right? So matlab pure liquid state, all of that has turned into vapor state. Technical definition of boiling is when the vapor pressure becomes equal to atmospheric pressure. This happens at certain temperature, so we call that, okay, this particular liquid is boiling at that point of time. It's changing the phase. Okay, so it boils at a constant temperature. So even when you boil it, like the mixture as a whole boils at that particular constant temperature. How do we differentiate it? Okay, so if you had a mixture of alcohol plus water, how do you separate it? So
Fractional distillation. Not fractional distillation.
distillation.
Different boiling points. Yeah, distillation.
Either like if it's small difference, you use fractional distillation, otherwise simple distillation ho jayega. Essentially, the principle is the same, right? So what do you
Same
do?
only.
You boil
I
it.
think fractional distillation is the term used when there are many, like this is only two, but if there are many compounds to be separated, then with very little difference, then we generally use fractional distillation.
Yes, when there's little difference in this. But the principle behind them is essentially the same. You boil the mixture, and the component that boils quickly wo vaporize hoke aa jayega, the other one's in liquid state. But when it comes to azeotropes, like some mixtures at some specific concentrations, ऐसे बन जाएगा कि they have the same composition in vapor state and liquid state. So even when you boil them, they essentially boil at the same constant temperature. So it becomes impossible to separate them by distillation. Okay. So azeotropes occur at
0.4,
what was that, Kaveri?
What is 0.4, 0.6?
That's just examples that I took. So composition same rahega in liquid state and in vapor state. So if mole fraction in liquid state in this particular solution was 0.4, 0.6, even in the vapor state, when you measure it, you'll find the same quantities of A and B. So essentially, this like what this means is even when you boil the mixture, क्योंकि vapor state में ही वही composition है, it becomes difficult to separate A and B. They're like paired up. Distillation say you won't be able to separate them out. So those sort of mixtures are called azeotropes. Like that's the main reason why we want to learn about them, because if your intention is to separate out parts of a solution, you don't want it to be an azeotropic mixture. Or if you want both the components to go into a reaction, or like basically if you want both the components to be together, then you ensure that it's an azeotropic mixture so that they don't accidentally separate out when you boil them and all that. So it's important to know, like if you have a pair of this thing, like when you have a binary mixture, when is that an azeotropic solution and all that. So this happens only at like specific composition at a specific temperature. This is the characteristic it takes on. So this is the definition. What do you mean by azeotropic mixture? The binary mixtures that have the same composition in both liquid and vapor phase, and they boil at the same constant temperature. They boil at a constant temperature. Okay. So
What is if there are two fluids which is an azeotropic mixture? Those two fluids, if you take with other two different fluids, then uska bhi azeotropic mixture hoga na? Like every mixture can have its azeotropic form.
yeah, like again,
Yeah.
specific conditions need to be met in terms of temperature, in terms of this concentration, but yes. So if you observe this happening, same composition in liquid and vapor phase, and they boil together at a constant temperature, then okay, that's an azeotropic mixture. That's why you call it constant boiling mixtures. And the main thing is like significance, importance of this is that it is not possible to separate the composition, the components by like even by fractional distillation, by distillation or fractional distillation. Basically, you can't use that technique.
What's this alcohol plus water you've written for what?
This I was like, I wanted to remind you guys of water's distillation and all that separation techniques.
Oh, so this is not really. Oh, I still don't.
When we say constant temperature, do we mean same temperature or?
Same temperature and at that particular temperature. If you
Huh?
have pure substance, उसका एक constant boiling point होगा ना. But mixtures में you have two different substances. तो पूरा mixture को boil करना है मतलब like पहले एक substance boil हो जाएगा फिर दूसरा substance boil होगा. So two different होगा. But if it is an azeotropic mixture, both of them boil together at one constant temperature.
So the same temperature, right?
Yeah.
Ma'am, I got disconnected. I did not understand like the fractional distillation wala part. Not possible.
Because see, the composition in liquid and vapor state same hoga na, and they are boiling at one constant temperature. So when you boil this with an intention of like एक component boil हो जाएगा फिर distillation से separate कर सकते हैं. It is not possible to do that with azeotrope because when you sit for boiling at that particular temperature, both the components will go into vapor phase, so you can't separate them out. So azeotropic mixtures में you have two different types of azeotropic mixtures. You have
1 second.
oh yeah. Arya, you took math and bio both, kya? Or is it like applied mathematics or something?
No, it's math. Good.
Liquid and vapor phase means like they boil at the same temperature, but same composition in vapor phase means what? The way they were in liquid, same way when they boil they are.
Yeah.
But like composition means what?
Composition is concentrations basically. So if it's like 40%,
Obviously, like concentration within the solution. So if the solution is liquid versus when the solution is in vapor phase, the concentration of the components remains the same.
yes. So yesterday you guys did a question also, right? Ki, solution may you have like a particular mole fraction. Like solution may you may have 40% A, 60% P. But vapor phase may you might have completely different concentrations. You might have like 30% A, 70% P. ऐसा हो सकता है. So azeotropic is में, so that is the characteristic. So liquid state solution में जो भी composition है, concentration 40, 60, 35, 65 जो भी है, vapor phase में भी the same, like the mole fraction, composition, concentration will be the exact same values.
Yes, when we say constant temperature, does it mean that the individual components also have a similar boiling point, or no, or like does that mean that when they are in the mixture, the temperature at which the whole mixture boils, that temperature we take into consideration?
Yeah, the temperature at which the whole mixture boils. So another characteristic that we didn't discuss till now, but which we are going to is when you have mixtures, the boiling point changes. Like for example, so this will happen whatever the solute may be. Like even when you compare boiling point of pure distilled water versus boiling point of say salt water, they're going to have different boiling points. You have some elevation and boiling point and all that. So even in this case, there's going to be like they're going to have a different boiling point as compared to if it was like pure A or pure B. So when we say boils at a constant temperature, yes, the temperature at which the mixture is boiling out. Okay, so we have two different types of azeotropes. You have minimum boiling azeotropes. And you have maximum boiling azeotropes. We'll do one at a time. Like we'll start with minimum boiling and then we'll do maximum boiling. Or do you want to do it as a comparison? Like divide the page, you can do that also. Similar points in both the cases, so let's do it this way. We have minimum and we have maximum boiling. So you observe minimum boiling azeotropes when you have a large positive deviation at a specific composition. And maximum boiling you observe when there's a large negative deviation. Again, at specific composition. Okay. So minimum boiling azeotropes के लिए you want a large positive deviation. So how do you figure out, like graphically? So positive deviation matlab uh, this is how the graph looks like, large positive deviation. So let's give it a big curve. So when you have a large positive deviation, so the point where the vapor pressure is maximum, like is curve ka maximum point, this particular point. So is composition pe this mixture will form the so this is the azeotropic composition is what we say. So minimum boiling isotopes के लिए you need a large positive deviation. We said it forms, like you observe minimum boiling at specific composition. So it is this composition, like the composition at which the vapor pressure is maximum. यहाँ पे the boiling point is minimum. Okay. So that is what, like minimum boiling point. So it's a minimum boiling azeotrope. Graph. Let's complete it again. The same thing.
So this is for positive deviation.
So if you have a positive deviation, like a positive deviation non-ideal solution, you will observe that at a specific composition, when the vapor pressure is maximum, like a curve cast maximum point, at that point, the boiling point of the mixture will be minimum, the lowest boiling, like the temperature is lowest, it will boil quite easily. So that particular composition, that's what we call as minimum boiling azeotrope. Because it's an azeotropic mixture, which is boiling at like jiska boiling point is minimum. So it's minimum boiling azeotrope. Abhi maximum, like in the case of negative deviation, क्योंकि ग्राफ नीचे जा रहा है, उसका minimum vapor pressure होगा. So that's why you get a maximum boiling azeotrope. If you have a large negative deviation, so T total इसका lowest point इस curve में, so जहाँ पे vapor pressure is minimum, so यहाँ पे minimum total vapor pressure है. So at this point, the boiling point is going to be maximum. So this composition, this is the azeotropic composition. And yeah, because it's the boiling point is maximum, you'll find the highest boiling point for this particular mixture at this composition. That's a maximum boiling azeotrope.
Miss? I didn't understand minimum boiling.
Okay, first of all, before we talk about this, do you understand what the connection between boiling point and vapor pressure is? Like, why are they inversely? Like, why do we have maximum boiling point at minimum vapor pressure? Or minimum boiling point at maximum vapor pressure?
Because if the boiling point is minimum, that means in the particular fluid there'll be more vapor pressure on it, right?
Correct. It can get into vapor easily. You don't have to heat it at a high temperature.
Yeah.
It's easy. So इसलिए, if the vapor pressure is low, boiling point will be like if the vapor pressure is high, the boiling point will be low, like inversely proportional. Okay. All right. Now coming to azeotropes. So azeotropic mixtures, or so you have a mixture like solution of two substances at a specific concentration. They would form such a solution where they boil at a constant temperature and the phase in liquid state, vapor state are the same, right? So
Can you say it again? Could you say that again?
So azeotrope, like basically when you have a mixture, there will be one specific composition. When the composition in liquid state and vapor state is the same.
Yeah.
So, even if you boil it, like they will both boil at the same constant temperature.
Yeah.
And they're constantly boiling, so it's not possible to separate them out, right? Now, this is different types of azeotropes. So they boil at a constant temperature, matlab, like you might have a minimum boiling azeotrope or a maximum boiling azeotrope. Like azeotropes just may boiling point becomes lesser, and azeotropes just may boiling points becomes higher. So where do you observe each of them? So minimum boiling azeotrope you will find for solutions that show
Lesser boiling point.
a positive deviation.
So lesser boiling.
Huh. Lesser boiling point. Lesser boiling point के लिए you need higher deviation. Vapor pressure ज़्यादा है. So it'll
तो
boil.
ही ज़्यादा escape होगा ना, मतलब तो ही easily convert होगा.
Yeah.
To gas.
Yeah. That is why the boiling point is at a minimum at a certain point.
But how is that related to the positive deviation? That like positive deviation is when AB interactions are weaker than the individual component reactions, right?
Yeah.
So vapor pressure in positive deviation will be more than the expected.
Correct.
Right?
Huh.
So
now take it one step further. If you were boiling the solution,
yeah.
will it boil at a higher temperature or a lower temperature?
What? No, higher temperature or temperature for what? Positive deviation.
Huh.
It will boil at a lower temperature because it will boil at a lower temperature, it is easy.
It's easy, so it
Matlab
boil
wo-
at a lower temperature. You don't have to give it a lot of energy to vaporize it.
Yeah. Yeah.
So there is one specific composition where the boiling point is minimum.
Specific composition of the two components in the mixture where the total boiling point of the mixture is minimum.
Total boiling point matlab you're not adding the
पूरा जिसमें हाँ समझा
boiling that solution. Yeah.
Yeah. And maximum one.
Maximum is the same thing. Now consider solutions that show negative deviation. Negative
It's
deviation.
not easily converting.
Yes.
So more energy.
Yes. So
But
boiling.
then how is that having lesser vapor pressure?
क्योंकि it's not converting easily ना, तो vapor pressure ज्यादा होगा कि कम होगा? Overall.
अगर ज्यादा होगा तो वो convert करने नहीं देगा ना.
But that's what we saw in the positive deviation ना. So vapor इतना आसानी से convert नहीं हो रहा है. Like you have very few molecules in the vapor phase because the conversion is not. Which is why the values of lower pressure are lower. Like the values of vapor pressure are lower.
Oh, wait. So does it mean that because the boiling point is higher, so there are very less vapor particles, so the vapor pressure will be lesser? Lesser? Somewhat.
Yes. Yeah. The other way around. Vapor pressure कम है, इसलिए the boiling point is higher.
Okay. So where they are coinciding over there is a maximum, or can you just make a line just like that, right?
So यहाँ पे curve है ना?
हाँ.
Curve है मतलब that like the lowest point of this curve. Like this is at this particular pressure, this is at this particular pressure, this is at this particular pressure. So the minima of this. Have you guys studied about maxima, minima? Differentiation, integration, calculus में?
No, we just started differentiation.
अच्छा.
Okay. We started continuity and differentiability chapter. उसमें अभी तक maximum minima नहीं है. I think that comes in applications or something.
They're all like related concepts, but yeah.
Yeah.
So when you have a curve, like when it's a parabola, it's kind of easy. Like सबसे lowest point is the minimum value.
Yeah.
So that minimum point of this particular curve. Okay, so that minimum point, so that the minimum total vapor pressure that's when the boiling point is maximum for that mixture, and that particular composition जो है at this point minimum पे, that's the azeotropic composition.
So at all the other points on the graph, it's not an azeotropic mixture, right? Or
No.
is it still an azeotropic mixture at the other?
So this would be a maximum boiling azeotrope.
No, मतलब बाकी temperatures पे at other points on the graph, is the solution still an azeotropic solution or mixture or not?
It's not. So it'll happen only at specific composition.
So only at that one point is it azeotropic.
Yeah.
Okay.
When we say it is azeotropic at one point, what does that mean? Like
One point matlab one particular composition.
so when it is of that composition, then it will be the same in the vapor phase also.
Yes. Okay. So yeah, this is what is all about, like ideal, non-ideal solutions. Isme again the kind of questions you won't get numericals. It's all completely theoretical. Like you'll have definitions. What is azeotropic mixture, or give reason type of thing for non-ideal, like positive deviation, negative deviation, examples, or like an application behind it. Ki, what is the expected vapor pressure if this shows a positive deviation? Is it greater than say 140 mm, less than 140 mm? That sort of thing. Right. So final concept in this particular chapter. So we'll talk about colligative properties. Okay. All right. Smera, Sanskriti, Kaveri, guys here.
Yes, ma'am. Yes, ma'am.
Have you guys heard of this word before, colligative properties? What do you mean by colligative properties? Okay, so colligative properties. So these are properties that only depend on the number of particles. So number of particles, matlab, like, okay, now since we are studying about solutions, concentration of the solution. So it does not depend on the nature of solute, nature of solvent. It doesn't depend on anything except, okay, how much of the solute is there, how much of the solvent is there. It solely depends on the number of particles. That's what are colligative properties. So 4 important ones that we're going to be studying today in context of solutions are, you have relative lowering of vapor pressure, So this is what we touched upon a little yesterday when we were talking about solids dissolved in liquids. So when you dissolve something, we discussed yesterday, surface pay the solute particles occupy. So the vapor pressure of the solvent reduces a little bit because of what you dissolve. So that relative lowering of vapor pressure is one. And then you have elevation of boiling point. Elevation of the boiling point. Depression and freezing point. And fourth one is osmosis. Osmosis and osmotic pressure. So osmotic pressure, like how much pressure, like how much that osmosis will take place and all of that depends completely only on the concentration. It doesn't matter whether you used NaCl or KCl, like what have you used, it only depends on the concentration. Solely depends on the number of particles. Yeah. All right. So once you guys are ready, we'll look at each one of them. They're very, very simple concept wise. Again, you have like specific formulas and numericals based on that. Okay. Guys, everyone switched off your video. क्या हुआ? Arya, Sia, Sanskriti, Kaveri. What happened?
Sorry, I got disconnected. What's going on?
Oh, so I was just checking, like everybody switched off your video. What happened?
Yes, miss.
What happened? Is there a specific reason? Yeah, ऐसे ही क्या हुआ? First one, lowering of vapor pressure. Any questions about like why the lowering of vapor pressure takes place? Why doesn't it increase?
Miss, I thought you would do it now, so I didn't ask.
नहीं, reason तो हमने discuss कर लिया ना. So now we'll be going further. We'll be quantifying it. So why is there a lowering of vapor pressure specifically?
Miss, does this have to do with the
Because of
negative?
solute.
Because of solute, yes. What does the solute do? Arya, you were saying?
This is this related to the negative deviation one we did.
No.
The graph.
So again, negative deviation, positive deviation is for like liquid solutions. यहाँ पे we are talking about solid solute added to a liquid solvent.
Ma'am,
Hmm?
Like I understood what colligative properties were doing, but can you repeat the definition of colligative properties?
Nothing. They're just like a set of properties that only depend on the number of particles that are involved. Either the number of particles of solute in relation to the number of particles in solvent. That's a very twisted way of saying basically the concentration or composition of this thing.
Miss, all these properties are for solid liquid solutions, or
We mainly consider it for solid liquid solutions.
Miss, there was another property that or something that you said yesterday is for
This one.
solid liquid.
Lowering of vapor pressure. That's what we were discussing yesterday.
Yeah.
Okay. So again, just a quick recap. Yeah. So if you have a liquid solvent, इसका एक vapor pressure रहेगा. And why vapor pressure happens is the liquid particles get into the vapor state, and that exerts pressure. Now, when we put a solute here, solute occupies spaces between the solvent particles. So some of the solute is on the surface also, which means it blocks some of the solvent particles from getting into the vapor state. So that's why there is a lowering of vapor pressure. Now, it does not, so this is a colligative property because how much the vapor pressure is reduced only depends on how much of the solute you're putting. Like how many solute particles are there. It doesn't depend on is it a polar solute, non-polar solute, is it an acid, base. Like it doesn't depend on any other quality other than kitne particles hai solute ke. So if there's so many particles of the solute, lots of blockage, lots of lowering of vapor pressure. If there's less amount of solute, less blockage, so less lowering of vapor pressure. That's the whole concept. Clear? Yahan tak? Okay. So again, lowering of vapor pressure, because here we are focusing on the solvent. We will apply Raoult's law again. So vapor pressure of the solvent is equal to, if it was pure, P naught of the solvent into the mole fraction of the solvent. Okay, so we are looking at lowering of vapor pressure. मतलब कितना कम हुआ. So that is change in the lower pressure, delta P. So again, I'm going to use simple this thing. Okay, let's say solvent is 1 and solute is 2. So then delta P1 is equal to lowering matlab P naught is greater. So P naught 1 minus P1. So that will be P naught 1 minus P equal to, so P naught 1 into X1. That is equal to, if I take P naught 1 common, 1 minus mole fraction 1, chi 1, that is equal to P naught 1 into chi 2. Yeah. So if you know by how much the vapor pressure has changed, you can figure out how much solute has been added to it. So chi 2 is equal to delta P1 by P naught 1. So this is one formula that you'll be using. Okay, so I'll give you guys 2 minutes. Have you followed this derivation? Kya ho raha hai? How did we get each step? So the main thing you need to be careful is the concentration of the solute is equal to change in vapor pressure of the solvent upon vapor pressure of the pure solvent.
Ma'am,
Yeah.
how did you get like the first thing? The delta P. Like rest I understood.
So delta is change in vapor pressure, right? So we're talking about lowering of the vapor pressure, by how much it is lowered. So that is change in vapor pressure is original vapor pressure when it was pure minus the changed vapor pressure, the lowered vapor pressure. So for example, let's say original vapor pressure was taking a random value 50 mmHg.
So like P01 is of the solvent.
Pure solvent,
And then when we add the solid solute into it, it becomes P1. So we need to find the
Yes.
change.
Correct. Okay.
So this you found out how much of the solute is present in the mixture, right?
Yeah. So
the
this mole
solution.
fraction, this mole fraction is that of the solute. That's why I've written solvent 1, solute 2, like so that there's no confusion. Kiska kya hai? Okay. Do you want to discuss all 4 of them, or should we do some numericals on this and then go to the next property?
Numericals.
Do like one numerical. So usually the kind of questions you will get, it won't be like, okay, if it's for 1 mark and all, you might get this, but more often than not, from the mole fraction, you'll have to find like molar mass of the solute or the molar mass of the solvent or something like that. So you have to go one step further. Okay. So we'll just do one question, you'll have a better idea, and then we'll go to the next one. Yeah. So an aqueous solution of 2% non-volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molar mass of the solute?
How is this related? Like completely unrelated thing they're asking. Molar mass. How do we find?
So once you know the mole fraction, you can find the number of moles, and once you get the number of moles, usse you'll get
Got it.
this thing. Yeah.
Also, 1.004 is P1, right?
So solution exerts this much pressure. So this is the P1. I just noticed this has another twist also. They haven't given P naught directly. Can you figure out what P naught could be? यहाँ पे?
2% non-volatile.
P naught. Vapor pressure क्या होगा? 2% volatile. They've given the concentration.
Of water.
Water? नहीं.
This is aqueous solution.
Right. So water
So
or vapor pressure.
At normal boiling point of the solvent. Normal boiling point मतलब when something is boiling, उसका vapor pressure कितना होगा? I think I just mentioned it in passing. Like technical definition of boiling is at boiling point, the vapor pressure of the substance becomes equal to the atmospheric pressure. This is a thing, remember. So when we are talking about something boiling, it means that uska vapor pressure has become equal to the atmospheric pressure. So here it exerts this much at normal boiling point of the solvent. मतलब without the solute, vapor pressure होना चाहिए था 1 bar. So P naught was 1 bar. After adding solute, P has become 1.004 bar.
Vapor pressure of water is 1 bar.
No, vapor pressure of anything is 1 bar.
What?
अभी atmospheric pressure क्या
Its
है?
boiling point,
Oh, yeah,
any
ETM
solution
would be
का.
1 bar. Correct. Correct.
I don't understand.
When it's boiling, the atmospheric pressure is equal to the vapor pressure. The atmospheric pressure is 1 bar. That's why vapor pressure also 1 bar.
Nothing see understand.
Where is it mentioned that it's 1 bar?
Atmospheric pressure is 1 bar only.
Acha, okay, okay.
What to do with the 2%?
2% is the concentration. Like
Ma'am, but
That
1
we know
ATM
what
is
to
not
do
equal
about.
to 1.
what's your 1 ATM is not equal to?
One bar.
It is more or less equal. Okay, let me see the relation between atmosphere and bar. One bar in 1 bar.
I still don't know what to do with the 2%.
More or less equal. Like for the sake of numericals, you can equate, like take interchange 1 bar 1 ATM. Very minor difference.
What to do with the 2%?
What is 2% given?
The mass percent.
Yes, 2% aqueous solution है. मतलब 100 grams solution में 2% is like 2 grams is the solute. Okay, if you want to be accurate for an approximate result, okay, let's interchange this.
1 second, ma'am. But like, so 2 grams is the solute and 98 grams is the solvent. Now, what do we do with that information?
Okay, have you noted down what all info has been given?
Yes, yes.
Okay, so example 1. So concentration is given as 2%. मतलब like 2% mass by mass. Also, you're given that the vapor pressure, the changed vapor pressure is 1.004 atmosphere. What is given? Bar. Okay.
Wait, so we are considering ATM and bar to be like the same, right?
Yeah, I can do that. If you want to be exact, you can use 1. What was that? 013. Okay. So what do you know about the relation between concentration and this one? So relative lowering of vapor pressure. So okay, what is delta P equal to?
P01 minus P1.
हाँ 1.013 minus 1. I think we have to use 1.013 because 1.004 is greater than 1 bar, तो negative नहीं होना चाहिए. So they intended for us to use 0.1.013.
Plus, if in like, will they give the value of bar, like which one we have to use, or
Again,
just have to
if
assume?
you look at the question, it said at normal boiling point, right? So you know that you have to take atmospheric pressure. So usually like 1.01, you kind of round it off to 1 bar or 1 atmosphere, right? But yahan pe, I said we'll use 1.013 because if you do 1 minus 1.004, you're going to get a negative value, which defeats the purpose. Like, so the concept is you have relative lowering of vapor pressure. Matlab, the original vapor pressure you should consider to be higher than 1.004. So I can't round it off to 1. Like that would be a huge error. That would give me a huge error. So difference कितना आ रहा है इसका?
0.009 bar.
9? Okay. हाँ 9 plus 430. Yeah. ठीक है. So this is delta P, and we know that concentration of the solute is equal to delta P upon P naught, right? So that is equal to how much? 0.009 upon 1.013, 9 by 1013. कितना आ रहा है?
0.008.
Okay. So this is the mole fraction of the solute. What do you mean by mole fraction?
Number of moles of solute by number of moles of solution.
Number of moles of solution. Matlab number of moles of solute plus number of moles of solvent is equal to 0.008. Okay. But we know the concentration. It is given in terms of mass by mass percent. So 2% aqueous solution matlab in 100 grams of solution, we have 2 grams of solute, right? Okay. Aqueous solution is given, right? So we know solvent is water. So basically in solution, we have 2 grams of solute plus 98 grams of water. Okay. So using this information, can you find the number of moles of solute and number of moles of water?
We can't find for solute, right? Only for
हाँ.
water.
क्योंकि we don't know what the solute is, it will be 2 by उसका molar mass. Water का?
I didn't understand this. What did you do?
Even I.
Okay. Do you understand यहाँ तक क्या किया हमने? This is mole fraction. So we just applied mole fraction का formula. Okay. Now mole fraction के लिए we need to we can use only the number of moles of solute solvent in the mole fraction का formula, right? but we don't know the number of moles yet. So let's go back to the information that we have right now, which is concentration is given as 2% solution. So we took that 2% solution. 2% solution matlab we can figure out, okay, like if we have 100 grams of the solution, usme se 2 grams is that of the solute. ठीक है? Kaveri? Makes sense? So basically, we have 2 grams of the solute plus 98 grams of solvent, which is water. यहाँ तक ठीक है?
Yeah. What did you do after that 98 grams?
इसके बाद, so this is the given mass. So now I'm finding the number of moles. So number of moles of solute कितना होगा?
वो कैसे पता?
So we don't know that. That's why I've kept it as 2 divided by m.
2 you got from that 2%. Oh no, yeah, 2% wala, no, 2 grams.
And number of moles of water, can you find out?
$98 upon 18, no? Yeah.
Say this is 249, 2 nines. मतलब 2 9 5s are 45. We're 40. 5.44 ऐसे, something like 5.4, right? So using this information, can you figure out what is the mole fraction of the solute?
Sorry, what is capital M?
Capital M is molar mass of the solute. Capital M हमेशा molar mass of that substance. Okay.
Yes, we write for molarity also.
Huh? हाँ, moles per liter molarity. ठीक है. So let's put here where M equal to molar mass. So figure out the mole fraction. So this will be 2 by m divided by total number of moles. Now this should be equal to what value did we get there? 0.008. Solve this equation and you'll get the value of m.
Can we do another numerical after this?
Yeah, sure. Would it be easier for you guys if you had a direct formula for molar mass? So the derivation follows the same method, but there'll be a lot more variables. So if you want, I'll give you that. Otherwise, we'll stick to this and you can work this out as well.
No, Miss, we'll stick to this because then that will be more extra things to remember.
Yeah, and there'll be a lot of like W1, M1, W2, M2, like. Yeah.
There's so much calculation for this.
The W1 thing, that's what we did in school also.
I'll give you both. Stick to whichever method you would find easy. If it's easy to remember the formula, use that. Otherwise, you can stick to this.
Would we be given such difficult questions like with lot of calculation?
Yeah, physical chemistry is all about calculation. You saw that in equilibrium and thermodynamics last year, no, CR? It's gonna be like that.
Yeah, but the question in exams were not that hard.
This is the first question you're doing it in this particular concept. Like a couple more, and then it'll get easier. Okay, Sia has already finished calculating. Oh, molar mass kilograms में आया. What substance is this? It's like the size of a small
Sorry.
child, 46 kgs.
Sorry.
Yeah.
Could you solve this now? I'm not getting.
Calculation part. Uh, 2 by m. I'll just take 2 by m to be x. Let's say 2 by m equal to some x. It'll get easy to solve. So x by x plus 5.44 is equal to 0.008. So x is equal to 0.008x plus 0.008 into 5.44. कितना आ रहा है? If I take this way, 1 minus 0.008x is equal to, how much is this? 5.44 times 42, 45, 43, 4352, and 1, 2, 3, 4, 5 decimal places. It will be 0.043. Okay. So x will be equal to 0.043 divided by 1 minus 0.008 will be 0.9. 43 by, so 2 by m is 43 by 992, which means molecular mass will be equal to 86, 132 मतलब 23. हाँ, 3 3s are 9. 23 point कुछ आ रहा है into 2 will be 46 point something. 129 is 30. 23.0 something आ रहा है. So it will be approximately 46 point whatever you get. So we can do like a quick summary of it again, like if once everyone finished calculating.
Can we take a break now?
We'll do one more question. I was thinking we won't be able to do the rest of the things. Let's get you guys confident with this concept, and then we'll have one more class for elevation and boiling point, depression, freezing point, and all of that. And there's no point taking a break now because like 5-10 minutes you guys will take a break for half an hour में class khatam. We'll just like finish off this concept, lowering of vapor pressure, do one more numerical. Okay, सबका हो गया? Like should I do a quick recap of what happened here?
Yes, ma'am.
Okay, so we were given aqueous solution 2% mass by mass, like solute का aqueous solution concentration है 2%. इसका vapor pressure was found to be 1.004 bar at boiling point. Okay. So we needed to figure out molar mass of the solute क्या है. Okay, so it's a solution and they specifically mentioned vapor pressure. Okay, guys, are you following? Are you listening? Should I continue?
Yeah.
All right. So interpret the question like solution hai at this much concentration, and they specifically said कि vapor pressure is so much or molar mass of the solute क्या है. So ideally, because they said boiling point, so basically at this temperature, ideally the vapor pressure should be equal to atmospheric pressure. And you already know that atmospheric pressure is not 1.004 bar, which means that vapor pressure has changed because of addition of this particular solute. So now you know the relation. The mole fraction of the solute is equal to delta P upon P of the solvent, P naught of the solvent, right? So plug the values to get the mole fraction. But mole fraction is not what you need. You need molar mass of the solute. So concentration will be the same whether you measure it in mole fraction, mass by mass, molarity, jo bhi hai, right? So equate the mole fraction that you got with this particular concentration. That's what we did here. Are you getting it? Make sense? So two concepts. One is from the vapor pressure, you can figure out what the concentration is. So this is step one. And step two, equate the mole fraction with the concentration that is given. So बीच में जो calculation किए थे, now this is mass by mass percent, right? So we converted that to moles because mole fraction के लिए we needed the number of moles. That's essentially what we did. Okay, right. Smira, Kaveri, Sia, Sanskriti, make sense?
Yes, ma'am.
Yeah.
All right, I said I'll give you the derivation, right? So if you want, you can note it down. If it's too complicated, let it be till here, and then you can use the concepts that you already know. What is the relation between molarity, molality, mole fraction, mass by mass, or else you can like use this formula also. Okay. So we got again 2 is solute and 1 is solvent always. So we got mole fraction is equal to delta P upon P naught. Now mole fraction is number of moles of solute upon number of moles of solvent plus solute, which is the total number of moles, which is equal to delta P1 by P1 naught. Number of moles is given mass upon molar mass divided by given mass upon molar mass plus given mass of the solvent upon molar mass of the solvent. So now rearrange this. How do we proceed? P1 naught into W2 by M2 is equal to delta P1. Let's just do it in a different way. Go to the next page because this is going to be kind of a big equation. Then iske baad just cross multiply. So you get P1 naught into W2 by M2 is equal to delta P1 into W1 by M1 plus W2 by M2. Open the bracket. delta P1 into W1 by M1 plus delta P1 times W2 by M2. So take this on this side. So you have P1 naught into W2 by M2 minus delta P1 times W2 by M2 is equal to delta P1 into W1 by M1. So W2 by M2 into P1 naught minus delta P1 is equal to delta P1 times W1 by M1. So W2 by M2 is equal to delta P1 by P1 naught minus delta P1 times W1 by M1. So if you want to find the molar mass of the solute, M2 will be equal to, so take this on the side, we get M1 W1 minus delta P1 divided by numerator में क्या है? We have W1 to so this is one formula. Can we simplify this further? So you have M2 equal to M1 W2 by W1 times P1 naught by delta P1 minus 1. Either this formula or this formula, one of these. Does this look more familiar?
No. Familiar to what?
You were mentioning schoolmates given us in terms of W1, W2 and all that, right?
Yeah, but I don't.
But
Was
not
it like
this.
this?
It
Yeah,
was
it
like
was not.
1000 by something.
It was like
So the 1000
M1
was
by
because it
W2.
was in kg.
हाँ.
Yeah, but उसमें P not थोड़ी था.
Yeah, this P naught P part was not there in it at all.
Not there, yeah.
Only M1, W2, W1, M2. Yeah, M2 is there, and then by 1000 or something.
Then that's a different formula because context matters, right? So either if you're talking about it in terms of lowering of vapor pressure, then vapor pressures will get involved. But if you're talking about it in terms of elevation and boiling point, depression, freezing point, then you have those KF, TF, KB, TB values, all of that. In any case, the concept, like logic, remains the same. So whatever makes sense for you guys, whatever is easy for you guys to follow, you can follow that.
It had this, it is same like this only. Only it's instead of -1, they have used LCM, and instead of delta P1, it's actual values like P
So
naught
they,
1
okay,
minus.
so delta P also they've substituted P1 minus P naught and they've simplified it essentially.
Yeah.
Huh. ठीक है. More mathematics there. Yeah. Let's do that because you'll be given P1 more than delta P. So let's do that. We're doing that, then I'll do it in a different color. So यहाँ पे let's do this. We have M1 W2 by W1. This will be the same anyway. This will be not minus minus P1. So we have M1 W2 by W1 times, if you open this bracket, ये दोनों cancel हो जाएंगे. So we have P1 by P1 naught minus P1. This is what we have.
Do we have to write the derivation?
Up to you. Like you won't be asked derivation, you'll be asked direct like numericals based on this concept, this formula. So either you can simply remember like this concept alone, and then depending on what is given in the question, depending on the situation, whether it's this one or molarity, you can work it out on your own. Or if it's easier for you to remember, you can just remember this formula, either or. One last question. So once you guys let me know, I'll change the screen.
Ma'am, could you go once to the previous slide? Yes, ma'am.
Okay. Question kare abhi? No. No, this is a much easier question than that because you're directly given the masses. You're not given mass by mass percent or volume percent and all that. We'll be able to do it. Okay. Smera, Kaveri, Sia.
Yes, ma'am.
Yeah.
Okay. Look at question number 29. Okay. So I'll start off with you guys. So vapor pressure of water at 293 Kelvin is 17.535 mm of H. So you're given P naught of water is 17.535 mmH. Calculate the vapor pressure of water at the same temperature, so you don't have to worry. When 2.25 grams of glucose is dissolved in 450 grams of water. So you need to find T1 is how much? When 25 grams. Do you guys remember the formula of glucose? Is dissolved in 450 grams of water. So basic thing that you need to remember is mole fraction of solute is equal to delta P1 by P01. So you already know P01. So you need to figure out delta P1. Usse you'll get P1. If you want to make things easier, you can also write it as P01 minus P1 by P1. Mole fraction also you can find because you're given the masses. Yahan se you can calculate the mole fractions easily.
What is the molar mass of glucose?
Molar mass of
Never mind.
yes, Arya got it. It's a little calculation heavy, but simple. Smera, like when you're given 17.535, try and round it off to 3 decimal places. So that'll give you a more accurate value ki kitna lower hua. But I can see like you also pretty much got around that same value. हाँ सही है. Nice. Smera and Arya got it. Rest of you guys. Actually, till where have you reached? Kaveri, Sia and Sanskriti?
Almost done now. One second.
Ma'am, I made an error, so I'm redoing it.
You like try and figure out, man. Like if you want, I can suggest some apps, or maybe if you have like resources for basic math.
Yes, ma'am.
Yeah, you need to figure out. See, again, like if it's the last step, okay, but if there's a calculation error in the first step, even though conceptually you do the whole question, final answer galat aa jayega. And especially in like competitive exams and all, that is going to be a huge disadvantage. Because final answer pura galat hoga. You won't even get step marking and all that.
Miss, if we like, if the final answer is wrong, but unit है तो मिलता है कि नहीं?
If it's a subjective paper, the marking scheme, like you have a specific marking scheme, you know, like for using this particular formula, itna weightage hoga, and for doing this step, itna weightage hoga. So you should get like part marking.
Because usually in school, Miss says ki even if you don't get like the answer, you should just at least mention the unit, because you never know that they might cut marks if you don't write. So kuch nahi ho to unit.
Unit to definitely needs to be there. What are you asking about? Like you got the number wrong, like in unit hai.
हाँ.
It depends, right? Like that's what I said. You have different weightage for different things. So if you did the whole question correctly, and last May instead of doing 2 into 3 6, you wrote 2 into 3 5, and then units or सब कुछ सही है, then you will get the marks for that. Like वो calculation error के लिए जितना weightage है, you will lose only that.
Maybe lose half or something.
Yeah, half or one. But first step में, like suppose you have to find the number of moles. उसके बाद like use
Yeah.
something else.
I got you.
पहले step में ही if you make it
Correct.
पूरा जाएगा.
Yeah.
See, I check, no, like your vapor pressure इतना ज़्यादा lowering नहीं है. 17.535 became 5305. Check calculations here. It should be a lot lower than that. Kaveri इतना ज़्यादा भी नहीं होगा. 17 does not become 3. Sia and Kaveri, can you guys tell me how you approach? Like, what did you do?
We needed to find a P1, right?
Yes.
So first I did, so like the number of moles of glucose, that would be 0.16.
Oh, 0.14 आना चाहिए था. 25 divided by 180, ना?
Yeah, right, yeah. I'm
0.8 around 1.4 के आसपास. Yeah.
Anyway, so like, so first I found the number of moles of glucose, then the number of moles of water, and then mole fraction of
Glucose.
Glucose, yeah, and then that is equal to 17.5 minus P1 by 17.5.
Yes. Again, don't round it off to 17.5. If they've given 3 digits, there's a reason for that. So take 17.535.
Okay.
Closer, Sia. Yeah. So the final answer you should get 17.437,438 के आसपास.
I'm getting only 49. I used the formula.
Okay. So, acha, you used W1, M2 and all of that. Okay. देखना पड़ेगा. Kavi, you definitely won't get 17.5. Acha, are you saying you're using 17.54 instead of 53?
No, I got 17.54.
Oh, you should get lower than 17.5.
Yeah.
Check the calculation, guys. But otherwise, conceptually, yeah, all of you followed the same steps, same method. You got the hang of it.
I took 5-3, so I got 4-2.
हाँ 4-3 का 4-2 हो गया यार. ठीक है. All right. Sanskriti, where are you at?
I'm still calculating.
Like
I followed the same steps.
N2, N1, like you took these
Yes,
values.
ma'am.
Okay.
Yes, ma'am.
तो फिर देख लो. Yeah. All right. So this particular thing, relative lowering of vapor pressure, I'll assign it to you guys. Kar lo this hafta. Next chemistry class, we should finish off solutions chapter. For alcohols, phenols, we'll start like one class after that.